Hey, so we're going to start up our second chapter of Trig in PreCalc. This is actually the second of 3 chapters. The good news is they get progressively smaller as we move through the course, but I'm sure you've noticed by now the first half of PreCalc is pretty much a repeat of Trig topics taken to a whole nother level, so experience a little more of that. This is the more algebraic component of the Trig course, so we're going to start off talking about trigonometric identities and trig trades. And we're going to start today with our lesson just simply simplifying trigonometric expressions using the identities we're provided. And we're going to talk briefly about cofunctions today as well. And then the next lesson, which is 5.2, we're going to talk more about verifying identities. Those are the ones that kind of felt like geometry proofs, but without the actual words associated with the reasoning. So here on the screen we have the concept of the reciprocal and quotient identities. So these are the identities that we've worked with extensively over the course of the last trig chapter. So sine is the reciprocal to cosecant, and then cosine is the reciprocal to secant, and so on and so forth. And then remember, tangent can be written as sine over cosine. Therefore, cotangent can be written as cosine over sine. So remember, those are all the nice swaps that we can do. And with your prior trig experience, you probably noticed that a lot of the trig trades that went on were swapping things out for sines and cosines, or whatever variety of sines and cosines they came up with. Remember, some algebraic components would come into play here. We're going to be doing a lot of common denominator work. We're going to be squaring both sides of equations. And then here, this screen talks about some notation. And sometimes I get even lazier with my notation. Sometimes I'll lose variables in my work just because I'm like going way too fast, and that's not a good thing to do, so I apologize if I do it in my work today. But sines, the function sine theta squared, sometimes they write it like this, so that way they don't have to worry about parentheses. Because if you just wrote sine theta squared without parentheses, it looks like just the theta is being squared, so you'd either have to put parentheses around the sine function, or they get lazy and just go sine squared theta, which means the same thing. And then naughty teacher is going to do a bunch of this, which is really, really wrong. I should have a variable, otherwise it's not a function, so my bad if I do that. Alright, moving along. I feel like I'm about to lose my voice, so let's hang in there. A couple more identities we have to become familiar with are the Pythagorean identities, and they are a derivation of the Pythagorean theorem. If we remember, cosine and sine are the x and y values in our unit circle, with the radius being 1. They could set up a Pythagorean theorem problem that says cosine squared plus sine squared equals 1 squared. And that's what this Pythagorean identity is right here. And then, fun fact, there's 2 more Pythagorean identities depending on what you divide the equation by. So if you take the original Pythagorean identity and you divide everything in the expression by a cosine squared. The equation, I should say. I don't know what I said. Alright, so if I look at my simplification, sine squared over cosine squared is tangent squared. Cosine squared divided by itself is a 1. And then 1 over cosine squared, better known as secant squared. So it's really just the same Pythagorean identity, but it's being divided by a common cosine squared. So here, what would happen if we divided this Pythagorean identity by a common sine squared? So sine squared over sine squared is this one right here. Cosine squared over sine squared is cotangent squared. They just reverse the order. Commutative property, we can do that. And then 1 over sine squared is cosecant squared. So these are all the same Pythagorean identity, and as long as you know the first one, you could derive the other 2 pretty quickly. But if memory serves me correct, I feel like we gave you all 3 of them on the formula sheet. So, speaking of formula sheets, here they are. And then if you look at, it says worksheet 30B here, I'm pretty sure it still is 30B. But what they did on this worksheet is they took all those Pythagorean identities and they rearranged the crud out of them. So like this one, if you subtracted cosine squared to the other side, you get sine squared equals 1 minus cosine squared. So basically it's just a series of manipulations of all 3 of those equations. You guys are really good at algebraic manipulation, so I'm not concerned that you're going to have a tough time with that one. Alright, so this is not a new concept. You can actually use Pythagorean identities to solve this problem. What we used to do in the last chapter is we draw it out in the quadrant. So between 0 and 90 degrees would be over here. And if the sine is 3 over 5 for a ratio, you do a little Pythagorean theorem or recognize that that's a triple. And then if we want to find tangent, that would be y over x, so the tangent ratio is 3 over 4. However, if you wanted to, you could use any variety of these Pythagorean identities to solve as well. So you'd have to work with fractions, of course. But like if you chose this one, remember how they gave us sine? So the sine value in that problem was, I think it was 3/5. So you'd write like 3/5 squared plus cosine, I don't know, squared equals 1. And then you'd subtract the 3/5 squared, which is 9/25. So 1 minus 9/25 is, let's see, 25/25 minus 9/25. Yeah, I should be able to do that, right? 16/25. So it says cosine squared is 16/25, which means the cosine is 4 over 5 when you square root both sides, which tells me the cosine value. So you could either then do sine divided by cosine, or you could remember that cosine, the x value, is the numerator of it. Was that easier to use the Pythagorean identity? No, but it's a nice algebraic way to prove something else maybe in your future. In college, they make you do a lot of things where you have to derive and prove formulas, so they don't really like you to just draw things out. When you're deriving and proving things, you have to have algebra with it. All right, so here, again, instead of doing the identities, I think we'd be more comfortable just drawing it out. Cotangent is 12 over 5. Tangent of theta is what they want. I don't really think we have to do much work here at all because cotangent and tangent are reciprocals. So, coffee break for a moment. Hold on. That'll surely help my voice. So the tangent value is 5 over 12. I didn't even have to draw that one. Alright, so here, sine is negative. Oh, what am I doing? I don't have to draw this either. Cosecant, reciprocal. Boom. Answer's -4. Alright, so, man, if only life was that easy. Now here they did give us a few more clues because I don't want simply the reciprocal anymore. Cotangent of alpha is -4 over 3. And then the other clue they give me is that sine is also going to be negative. So a place where tangent and sine are negative would be down here in quadrant 4. I'm going to draw a triangle that probably won't make sense, but the cotangent is 4 over -3. I'm going to have to make that vertical leg -3. And then this is not Pythagorean triple, so be careful when you do Pythagorean theorem. Square root of 16 minus 9 would be square root of 7. Positive value, this is going right. So the cosecant would be, where are we at? 4, nope. Oh, Bruso. Back up. I didn't even label the triangle right. Forget it. Alright, cotangent. It's -4 over 3. So try this again here. 4, -3. That's better, that's better. This time it is a Pythagorean triple. Good night. Alright, and then the cosecant, instead of -3 over 5, it's going to be -5 over 3. For cosecant. Oh my gosh, I don't even know what I just said. Maybe I shouldn't be recording this lesson right now. Alright, secant of A is -4. Cosecant is positive. Alright, so secant is friend to cosine, so he's negative, so it's one of these quadrants. Cosecant is friend to sine, so that's up here in quadrant 2, if he's positive. Alright, secant -4 over 1, which means this is a -1 and 4. Alright, this time not a Pythagorean triple. So square root of 16, -1 squared is still a 1. So square root of 15 is the length of the other leg. And it is positive because it's a vertical, going upwards here. And then they want tangent. So the tangent of alpha is -square root of 15 over 1, or -square root of 15. Oy. Good night. I just keep saying good night, but guess what? It's really early in the morning. Okay. Let's talk a little bit about I think this is where we start talking about our co-functions. No, not quite. Oh, even and oddness. Yes, yes. So, remember that sine is an odd function and tangent is an odd function, but cosine is an even function. So we have to remember the algebra rules for even and odd. And on my notes, that's what I would write down a little bit. I would say that sine is odd, cosine is even, and tangent is odd. Alright, so remember for algebra, if you have an odd function, that means if you were to plug in a -x into the function, you get the opposite function. So for us, if we were to plug in a negative value for theta into sine, that would produce a negative sine value. And here they have a little description of that. I mean, if you think about sine being the y value, if you were to look down here, remember that would be like a negative in front of the function, like a vertical reflection. You're still getting the same x value. So this is their little visual demonstration of it. They're using alpha instead of theta. So sorry about my confusion here. I'm going to keep using theta though. So the same thing's going to happen for tangent. If you evaluate tangent at a negative angle, it's just going to be the reflection of that. So, hello, tangent. Negative tangent of theta. And then cosine is the weird one. Because cosine is even, you're going to get the same value out again. I mean, if you have the negative angle here, so instead of positive 30 degrees, you go negative 30 degrees. Your cosine value is not going to change. So remember, that was a property of even functions. If you were to evaluate it at a negative input value, you just get the original function back again. So take that for what it is. It's going to help us with some trading. Here's a nice graphic visual, and it has also the reciprocal functions there as well. Co-functions. So when I first learned as a small child about like sine, cosine, tangent, cosecant, secant, cotangent, I was really confused why sine and cosecant were reciprocals of each other, and how sine and cosine, like, I felt like they should relate to each other in some way, and I didn't learn that they related to each other in some way until I took a trig course and then realized they were called co-functions. So you might have noticed this in the unit circle. When you look at the 30 and the 60 degree angles, they have almost the same ordered pairs, but the sine and cosine are opposites, and that's the cofunction property. So the sine of an angle is the same as the cosine of his complement. And your notes have this really crazy, like, they're using pi over 2 instead of 90 degrees, but if I go back to like little kid style complement rule, the complement is how far away from 90 degrees it is. So sine and cosine have a complementary relationship. Tangent and cotangent have a complementary, also a reciprocal relationship, but complementary. And then secant and cosecant. So therefore the prefix of co, meaning co-function. So they do have a relationship, see? This is not on our blue sheet, but there's a note here that we don't intend to ask you about the co-functions on a test. Frankly, I just want you to know for my math team kids out there, plus, going on to calculus, and then of course for your SAT test. So here, this question is a little strange, because the formula is, if for complement, it's how far away from 90 it is, so it has to be the 90 degrees or the pi over 2 minus the angle. Now notice this seems a wee bit backwards, yeah? So if something's backwards in algebra, what you can do is you can factor out a negative, and that changes everybody's signs and allows you to reverse the order. So what we have here is a cotangent with a negative inside of the angle, and remember our oddness of cotangent says I can bring that negative out in front of the function. So if I'm trying to evaluate the cotangent of what I thought was like a co-function here, it's kind of the same thing. So it'll be the tangent of theta, but I'm going to have to throw a negative in front of it. So I think there's actually a problem coming up on your notes here. Or not. There's a problem on your notes. It says I'm going to insert a slide here. Or not. It says the secant of beta, I use beta just for fun here, is -2, and they want you to find the cosecant. So it does have that co-relationship. The problem here, they want not cosecant of beta, back up. They want the cosecant of beta minus pi over 2. So this is the same issue that we had in this example here, where it's backwards. So what we're going to need to do is factor out the negative from here. And then when you factor out the negative, you can reverse the order. So pi over 2 minus beta. So with that negative pulled out in front of the angle, remember cosecant is like sine, so it's odd, so this negative is going to come out in front of this. So it's negative cosecant of his complement. So if the secant was -2, negative cosecant will be +2. So we're in the back of our notes for 1B, and here we're going to start the simplification process. So remember, we have to use a lot of our algebraic techniques. A good start for pretty much all these problems is to look for how you can trade into sines and cosines. But that also includes that Pythagorean theorem sine and cosine identity. So keep that in mind. Lots of algebra simplifying. You might need to factor. You might need to get common denominators. We're going to be using the conjugate property of factors. And, you know, when we get to the verifying identities, it's a little easier because you know where you're going to end. But, all right. So this question here, I have cosecant x times cotangent squared plus 1 over sine. So I'm going to use that technique where I just switch everything out for sines and cosines as far as I can see. So cosecant, I'm going to trade for a reciprocal, 1 over sine. Cotangent squared would be cosine squared over sine squared. And then we're adding that to 1 over sine. So this fraction here is cosine squared x over sine to the 3rd power. And I'm trying to add two fractions together, so the only algebra manipulation I can think of is to get common denominators. So I need 2 more sines in this fraction, so I would multiply numerator and denominator by sine squared. And then this common denominator would allow me to add these numerators together, and I'd get cosine squared x plus sine squared x over, kind of weird, sine to the 3rd power. And the other trade that seems a little obvious now is cosine squared plus sine squared. That's really just a 1. So I could call this 1 over sine to the 3rd, but probably a more simple way to say that would be cosecant to the 3rd power. There we go. And again, sometimes it's hard to know when you're done. The idea is we don't really enjoy having fractions in our final simplified answer, and I surely don't want to have like fractions that haven't been added together. All right, so here my algebra instincts are kind of kicking in, and I'm feeling like I should distribute this cosine. Let's see. So cosine x, while I'm rewriting it, let's trade tangent out for sine over cosine. And then we kept distributing cosine over here. So this is cosine x times cotangent is cosine over sine. So in this fraction, the cosines cancel. In this fraction, they don't. So I have sine x over 1 plus cosine squared x over sine x. So I don't really like to have uncollected denominators here. Let's get a common denominator of sine. So this fraction is going to be multiplied by sine over sine. So now I have common denominator of sine, but I do have, sine squared x plus cosine squared x over my denominator. And then remember sine squared plus cosine squared, that Pythagorean identity, that's just a 1. So I have 1 over sine, which I'm going to save a little space here. That is cosecant. Lovely. Alright, this is a hot mess. Now, it is currently written as a fraction, but it's definitely not simplified. So, let's take a look at, you know what, this is interesting. Secant is 1 over cosine. So, if this right here is traded as a 1 over cosine, then sine times 1 over cosine is just tangent. So I have tangent x plus another tangent x, interesting, over, you know what, I don't know if this is the right way to do this, but I don't care. I'm going to break up the fraction. I'm going to write cosecant x tangent x underneath each of these. Well, I guess I didn't have to do that. That was dumb. Try again. Let's call that 2 tangent x in the numerator. 2 tangent x over cosecant x tangent x. So now, tangent, one of the tangents will cross cancel. And I have 2 over cosecant, which is a little strange because cosecant is just a reciprocal sine. So I'm just going to trade that out and say 2 sine x. That looks about as simple as I can get. All right. And, you know, fun fact, it's not even the way I did it when I did it on my notes originally, so that's the good news, is you don't necessarily have to do it the same way your neighbor does. Still get the same simplification. Okay, the Pythagorean theorem identities list. This feels like that's one of those. So if you look at your list of all those manipulated Pythagorean identities, 1 plus tangent squared is secant squared. So I'm going to trade that out for that denominator. And if you're not really sure what you're looking at, what you can do is you can trade them for their sine and cosine reciprocal functions. So cosecant squared is 1 over sine squared. And then we're dividing it by secant squared, which is 1 over cosine squared. And then remember, when you divide fractions, you end up flipping the second one here and changing it to a multiplication problem. So now we're going to have cosine squared in the numerator over sine squared in the denominator. Methinks that is just secant squared. No, it's not. My goodness. Cotangent squared. There we go. Cotangent squared. That didn't feel right. Alright. This next question looks a lot like an algebra question where it's a binomial times another binomial, so I feel the urge to distribute. Let's do that. So secant x times the cosecant x, and then secant x times 1, tangent, so minus tangent x times cosecant x. You know, I'm looking at my work for this question. Should have warned you to write really small if you're writing along with me. And then negative tangent x. Alright, so this is obviously not pretty to look at right now. Let's trade these out for their sine and cosines. So secant, yuck. Alright, this is 1 over cosine, this is 1 over sine, so what we have here is 1 over, you know, I'm going to hold off on trading anything there. Go to the next term for a moment. If I need to trade something, secant can be 1 over cosine. Alright, I'm going to write myself a few notes, see what direction I want to take this. Tangent is sine over cosine. Cosecant is 1 over sine. Well, that's interesting. And then this is sine over cosine. So everything in my expression right now is a fraction. And the only one that has any cancellation is this one where the signs would cancel. But I do notice, like, if I look through my problem, I'm going to need to keep all my denominators. So instead of canceling everybody, I'm going to keep all of the denominators and just give extra denominator pieces to the ones that needed the common denominator. So we're going to hit this one by sine x over sine x, and this one by sine x over sine x as well. That was tricky, huh? Alright, so this is 1 plus, this numerator is just going to be a sine x, minus this numerator is also a sine x. Alright, so we're in the middle of creating our numerator here. Sorry, I fixed it. I had a tech issue for a moment. We're good. Alright, minus sine squared x is the numerator to this last fraction. Now, all of this is being divided by sine times cosine. So when I look at the algebra, the positive sign and negative sign are going to cancel each other out. And I end up with 1 minus sine squared. So 1 minus sine squared, sorry, I keep getting interrupted. That's what I get for recording in the middle of my morning. That's a variation of the sine squared plus cosine squared equals 1. So that is cosine squared. And then, if you have sine times cosine still in our denominator, cosine squared is like cosine times sine, cosine times cosine. So one of the cosines can cancel out. And you still have cosine over sine, which is our friend cotangent. There, I got it right this time. Alright, so I think when I originally keyed that up on my notes, I didn't do it in that fashion, and that was probably the most efficient way to do it. The way I chose was less efficient, of course. But it was super exciting, so you can look at my notes if you want that. Cotangent squared plus 1 is a trade for cosecant squared. And then secant squared minus 1 is a variation of one of those Pythagorean theorems, and that is, what is it? I always forget. Tangent, right? Tangent squared. That's why we have formula sheets, so we don't have to think that hard. And then cosecant squared is like 1 over sine squared. Tangent squared is sine squared over cosine squared. These sine squareds will cross cancel, and I have 1 over cosine squared, better known as secant squared. There's the simplest version. That one wasn't too bad at all, was it? Alright, number 11. When I originally did number 11, it took me forever to figure out how to get the answer I was supposed to get because I had need bifocals and I didn't see this random +1 off to the side, so my bad. Alright, so when you have a denominator that's a binomial, and it's not a Pythagorean binomial like one of those identities that we've been using, if you want to create one, you're going to use what's called the conjugate. So the conjugate to 1 minus secant, or 1 plus secant squared is 1 minus secant squared. Or secant, excuse me. And you can multiply a denominator of a fraction by whatever you want, as long as you also do it to the numerator. Looking ahead of my notes, I think I'm going to do one more trade while we're at it. Tangent squared, that is a Pythagorean one, isn't it? I think that is, yeah. Yeah. It's 1 minus secant squared minus 1. Secant squared minus 1. There we go. Is that right? I gotta go back and look for a minute. This is the one I always forget. Secant squared minus 1. Alright. So, up here in the numerator, I have quite a hot mess, frankly. Down in the denominator, however, I'm going to write this 1 in front so I don't forget it. Oh, I'm going to pause for the pledge. Okay, so I just had like an epiphany in the middle of the pledge. You're going to hate me, but we're going to erase what I just did in blue. Forget that. I'm going to keep the secant squared minus 1. I'm going to trade that out, but I'm going to keep it as a factor set. So secant squared minus 1 is like a difference of two perfect squares if I factored in. So that's going to factor into secant plus 1 and secant minus 1. What an epiphany, right? So my denominator on this fraction is still a 1 plus secant, which if you think about the commutative property, a 1 plus secant, these are the same thing. So they can cancel in that fraction. So remember, don't be like me and forget that you have a plus 1 over here. You have a 1 plus secant x minus 1. The plus 1 and minus 1 will be gone because they'll knock each other out, and the answer is just secant x, which is the actual answer, so go us. What I was going to do with the conjugate thing, I mean, it would have worked. I would have had like a lot of extra work and ended up canceling a whole bunch of stuff that I didn't need in the first place, so my bad. Alright, so the cofunction property we had in the front of the notes, remember, cosine is a cofunction buddy to sine, so the cosine of a complement is the same as the sine of the original angle x. So there's that trade. And then cosecant is 1 over sine. So if you take sine x and you divide it by 1 over sine, that's the same thing as multiplying by sine. So this ends up being sine squared. And then over here, I'm going to keep it as cosine squared because that looks pretty. I know what sine squared plus cosine squared is. That's a 1. That was actually a really nice one. Aww. But not all terrible, right? 1 plus tangent squared. That feels like one of my Pythagorean ones. It is secant squared. Ooh. So this is secant squared. And if I'm multiplying it by cosine, that wouldn't be too bad if I remember that secant squared is the reciprocal of, so it's 1 over cosine squared. And think about this fraction, you're going to have a little bit of cross cancellation. One of the cosines will cancel, so this is just cosine down here. And 1 over cosine, better known as secant. Let's see, another not so terrible one. It's just, you know, it's how attuned are your algebraic instincts. That's the issue. And, you know, obviously I've been doing this for a long time, so I have a lot of algebraic instincts that pop up in the middle of a manipulation question, and you guys are kind of new to it, so just go with the flow. Alright, this next one. This is the question where I have to start thinking about the conjugates, because secant and tangent, like, they're not very exciting as a subtraction problem, especially if they're not squared. So what if I were to multiply this fraction, numerator and denominator, by the conjugate, which is secant plus tangent? And this is totally legal as long as you do it to both sides of the fraction. So our numerator, I feel like I'm going to go ahead and distribute the cotangent. So I have cotangent x secant x plus cotangent x tan x. My denominator, however, remember how awesome conjugates are when you multiply them together? It's like a foiling problem, but the middles cancel out because they end up being like plus secant tangent minus secant tangent. So I'm not even going to bother with the inside parts of the foiling method or the distribution. So secant squared is secant times secant, middles cancel, and then I have minus tangent squared. That sounds familiar. Secant minus tangent. That's something, isn't it? Let's check. Secant minus tangent is 1. Well, that's exciting. So this denominator is just a 1. This numerator, however, is a hot mess. So the cotangent is cosine over sine. Secant is 1 over cosine plus, and then cotangent times tangent will just cancel out to a 1, yes? So we have 1 over sine, better known as cosecant, plus 1. And that's about as simple as that one's going to get. I suppose, let me think for a minute. I suppose we could guess we could get common denominators, like multiply, this by sine over sine, but I don't really think that's going to make it prettier, so I'm just going to leave it like this. This is the annoying thing about grading simplification questions, because like if your neighbor simplifies it to one more step than you did, like how do I determine who's right and wrong? I don't know. It's my problem, I guess. All right, here, cosine. That's nothing fun. I'm just going to write it. Tangent and sine. I'm going to rewrite tangent as sine over cosine. And then sine, of course, is just sine. So, if I think about, I'm going to want to add these together with common denominators. This fraction has a denominator of cosine. So what if I was to go ahead and provide a common denominator yonder? So this gives me cosine squared. This is sine times sine, which is sine squared. My denominator is now a common cosine. That is our buddy, the Pythagorean identity. So that's a 1 over cosine, better known as secant. Well, that really wasn't too bad at all. And that's a good ending to our lesson. That's a very typical simplification question. So if you get stuck, maybe jot down the algebra techniques that we use. So common denominators is a big one. We did a little factoring. We saw the difference of squares factoring pattern. If you have a binomial in your denominator that isn't squared, we tried the conjugate to get some Pythagorean identities showing up. Lots and lots of trades. So it's almost the algebra that stops kids from having fun here. So don't get bogged down by the algebra. Just think about all the techniques that we've used. And good luck.